Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is part of the series on circular motion, the second section on variable angular speed, and in this we look at motion in a vertical circle for the first time. Let's consider again a particle moving around a circular path. We're familiar with the idea of measuring its speed rather by considering the angular speed, and that's denoted alternately by omega or by theta dot being the rate of change of the angle that's developed from the initial position. So we're familiar with d theta by dt abbreviated to theta dot. Now we'll have occasion to see in a moment the use of the second derivative d2 theta by dt2, which, surprise surprise, is denoted by theta with two dots on the top, or you could also represent it with an omega with a single dot on the top. So what happens when we have angular speed? We know already that the linear speed is r theta dot. That doesn't change. Its alternative form is r omega, and the radial acceleration is still the same, v squared over r, or r omega squared, or r theta dot squared, according to which is the most convenient in the context. But there's going to be a tangential component too, because the speed is actually changing. Now the form of that tangential component is difficult to derive without the use of calculus for trigonometry. So here I'm simply going to quote the result. But there you are. In the general position where the speed is changing, you still have the same r theta dot squared, or v squared over r, both equivalent and unchanged, but in addition you have a tangential component which is of the form r times the second derivative of theta. In resolving using f equals ma, if you use the tangent, you have to bring in that alternative expression. But it turns out that for our purposes there's a very convenient way of avoiding having to do that. Let's consider then where we've got to. If we look at the idealized examples from the section in constant angular speed, and think about bringing in more realistic models such as the inclusion of friction or air resistance, then at that point you have to take account of an angular speed which will not be constant. In general, you'd expect it to be slowing down, so d theta by dt would be negative. Another example we can consider, which is very, very conveniently simple to develop, is motion in a vertical circle, where again we carry on the same assumptions about no air resistance. But the weight of the object needs to be taken into account, in that it's a force which will affect the value of the angular speed. So we would expect the angular speed to change. In short, the consequence is a variable speed. Let's consider a very simple case which brings out probably the most important simplification in the problem, which is thoroughly legitimate, as we shall see. Let's take a particle of mass 2 kilograms attached to a light rigid rod of length 0.9 meters. There you see a picture, and the other end of it's fixed at a point O, and it's in a vertical plane. The particle is released from rest at a point O, which is level from a point A, which is level with O, as you see there, and it falls in a circle down to B. We want to find the speed of the particle when it reaches B. Now, self-evidently, this is a problem with a variable speed, because you'd expect it to accelerate away from A from where it leaves at rest. It starts at rest. So let's look at the force diagram for this situation. Now we need to put the force in a general position, not at the beginning or at the end, otherwise we won't appreciate the general situation. We see that for a model which doesn't involve air resistance, there are only two forces acting: the weight, which is 2g in this case, and the tension. That's what keeps it in the circle. I've shown also the velocity along the tangent with a different arrow. Now when we consider what's going on here, we can look at it first from the point of view of energy. if we look at it from the point of view of energy, we can appreciate that we start with zero kinetic energy and we finish essentially with an energy which we're trying to determine, because that really is what it amounts to if you're trying to find the speed at the lowest point. What about potential energy? Well, clearly there will be a change of potential energy because we've got a force of gravity involved, but there's also what would appear to be a spanner in the works, the tension, which doesn't yield to a potential force. It's another contribution, and we would have to consider the work that it does. But look, all the time when the particle's moving, its velocity, which is along the tangent, is at right angles to the radius, which is the direction of the tension. Now the consequence of that, which is most important, is that the tension does no work. That really is significant, because it means to say that we can deal with this problem in terms of potential energy and kinetic energy alone when applying the work energy principle, because T doesn't contribute. So I say again, because the motion of the particle is at right angles to the direction of T, it does no work. So there we are. That summarizes that. Now that use of the energy principle avoids the point of difficulty I mentioned before, that you don't need to resolve along the tangent, but that's to tell the story before we get there. So to sum that up then, energy is conserved with this model. So we can do this by energy. We can say that for the usual energy balance, initially there's no potential energy if we take no kinetic energy, because it starts from rest. And if we take the zero as at B for potential energy, we look at the height lost, which is the 0.9 times the mg as usual. On the other hand, at the bottom, B, there'll be zero potential energy, but by that time it will have required kinetic energy, half mv squared, and v is what we're trying to find. Well, once we take the zeros out, you can see that the m's cancel, and basically you've got an equation which allows you to get v squared in terms of the half and the 0.9 suitably reorganized in the equation. In fact, v is the square root of 1.8g. So taking that v is going to be positive in the situation we've drawn, then we take the square root of that, which turns out to be quite simple, 4.2. So the speed at the bottom is 4.2 meters squared. That's 4.2 meters per second. Well, that shows how the energy principle can be useful in a problem where there are other forces which you would think would complicate it, and in fact, as we see in this situation, it doesn't. Now the question goes on to ask a bit more. It asks us to find the tension in the rod when the particle is at B. Now that has to involve forces, so let's draw a force diagram. There we are. It's a straight up and down T and mg at the bottom, and we've got the acceleration v squared over r corresponding to the speed v to the left. Well, we've just worked out v squared. It was that 1.8g. So there's the diagram again with the 1.8g in. And so now we can apply F equals ma along the vertical line. So taking positive as upwards, we've got t minus 2g as the force, and the mass times the acceleration is the 2 times the 1.8g over 1.9. So rearranging that and using the usual g as 9.8, the calculation gives us 58.8 exactly in this case. So we can finish by saying that the tension in the rod is 58.8 newtons in context with the units. And again I stress, the magic thing about this model is that the tension is real and effective. That's what keeps the particle in the circle, but it doesn't contribute any work. That ends this first video on variable speed in circular motion. The next in this same series will be more of the same, and I hope to be with you later to explore that.